the private environment that exists, there's a hustle for so many people, and there's always a need for something new. So it's a hustle, it's natural. Because government doesn't give you anything. It means you don't rely on government for anything. When you don't rely on government, you actually
Welcome to demos for the Hardcore Systems Hackathon. Woo! We have 10 wonderful projects for you tonight. Looking forward to hearing from Rohan, who claims to have created a new optimization algorithm that will free us from backprop forever. A request, if you are presenting, please join the Zoom. I sent that over both Slack and Particle, and share your screen with the Zoom while you're presenting. That'll let us get a really high quality video of your screen so that when we make a video of everyone's presentations, you can watch it in technical detail. So let's hear it for Rohan, first presenter.
So backpropagation is the primary algorithm which we use to train language models today. But if you look at language models, there's something weird about the way we pass labels around, right? So we're trying to predict token n+1 from token n. And what we do is we forward pass token n all the way up, and then we backpropagate from token n+1 down all the way over here, right? We basically take the diff between what it predicted and what the actual token n+1 is, and then we backpropagate that. But this feels kind of redundant. It feels like there should be something that we could optimize here, considering the fact that we forward pass all our labels as well. We forward pass token n+1 and n+2 and so on. So maybe there's a way we can take advantage of the fact that we're forward passing our labels to compute some kind of local gradients to get rid of backpropagation. So today I experimented with one idea I had for local error propagation. So the way this works is that we, for each token, we compute some local representation that we use to try to predict the embedding for token n+1 at that same layer, and then we backpropagate just into this layer. So at each of these individual layers, we calculate a local gradient between these two, and then backpropagate into this embedding. But critically, we don't backpropagate all the way, and what that means is that now we can parallelize each of the error signal, each of the error gradient computations that happen across all these layers. So just to look at a couple of results real quick. So when we're in the original setting, when we're just in like the backprop setting, right? Traditionally, when you're just training this language model, of course you start out with like this high loss, and over the course of training you go down to 0. With the local error propagation, instead what we see is like there is like some sense of learning, but like it's really not that much. Again, this is like the lower bound here is 10.74, so it's going from 10.84 to 10.74, so it's not really learning. But if we look at the local losses at each layer, for layer 1, 2, 3, 4, it does seem to be learning something in there. So I was asking myself, like, what might it be that's causing the language model to not learn anything, to only learn a little bit, like what's this lower bound? So then I decided to throw the backprop back in there. So this is like backpropagation plus local error propagation, and it like actually learns back down to 0, and we can see that like the local losses also learn like pretty smoothly and nicely. But again, like this is redundant, like we want to get rid of backprop. So like what's really bounding us here, I thought about this for a bit, and then I realized I'm not computing the gradients on the final, on the very, so like this is what we just did, right? Local error propagation plus backprop, right? So yeah, but that's like obviously not what we want to do. I realized I was not computing gradients on the language modeling head. So what we do then is that like we compute all these local errors, but then also for each of the transformer layers, but then for the final language modeling head, we also have to compute a gradient. And again, this can still be parallelized. It's not some weird backprop thing. It's just computing like a local gradient at the final language modeling layer. And what we see when we do this is that, once again, the local layer losses descend pretty healthily, and the language modeling loss also critically learns. It goes from like beyond 10 down to 2. It's not training as fast as the other like the backprop setting, but it is still trained down to 2. So yeah, I mean, it seems to be learning without us having to backprop anything. So this is like what we're actually computing here again. I can go through code if people want, but like if this works, if this scales up to bigger data sets, if this generalizes, then basically that means that we could like replace backpropagation, and like I think probably that's like a 6x flop saving or something like that. So yeah, thanks guys.
I'll get Ash first. So would it be fair to say that you can go one step beyond this, and if every layer is performing a transformation only within its own context, then we don't need n layers. We can just stack the same layer on top of each other, and every one of them will be performing like one stateless transformation, so that we kind of have this runtime ability to change depth, and every layer is just responsible for contextualization of information, which is kind of the primary purpose of most embedding models. Would it be like a good idea to test that, or you see challenges?
Maybe, I think, so like what you're saying is that like we pull all these layers to the side and then we like sum them up at the top or something, right? Like we each of them compute independently and then we sum them up or something like that.
Just delete all of them except for one, and then replicate that one many times, and then...
I think this would be hard because like the whole, like what we find empirically in transformers all the time is that like there's like there's a gradient where like there's like this graph where like semantic representation starts really low in like the early layers, and then like close to the penultimate layers it goes up a lot, and you replace a lot of really rich semantic features, and then it goes back down at the final layer when you actually try to predict something. And I feel like getting rid of the intermediate layers would lose a lot of the expressivity there probably. I guess one more question. Yeah.
Instead of having the red arrows, the data red arrows that go all the way to the top being deterministic, could you just use a sampling function or a randomizer such that like you would reduce the backpropagation cost of doing like the compute? In a way, can you just quantify the loss in some way that allows you to skip additional work as a function of the data set size?
I don't think so. I mean, so there's like directed feedback alignment, which sort of sounds like this, which is like this algorithm that, it's like without, there's no backprop in it. But they do this weird thing with like, random gradients or something like that. But like this operation is not that expensive. It's fully parallel. You can parallelize this alongside each of these individually. It's just long over here, but like, it's not actually like you don't have to do like long distance kinds of things, right? Like you can have separate targets that you just replace up here, n+1, n+2, n+3, etc. Cool. All right, awesome. Thanks, guys.
Back in 2018, there was a research subfield around this kind of idea. DeepMind did a paper, but there's also a paper called Deep Neural Networks via Local Errors or something.
Yeah. It's still a thing, I had a couple papers pulled up that did something similar.
There was a Narek's workshop in like 2018 or 2019.
I think this is the reason why it's fundamentally different now is that in the autoregressive language model setting, you're forward passing your labels, right?
Yeah.
Which gives you the ability to do weird different things.
Very cool. Okay, so that was replacing backprop with a local layer objective. Up is Sasha with GPU and metal backend for Gigagrad. Let's hear it for Sasha. Are you in the Zoom, Sasha? Okay.
Yes,
Make sure you guys screen.
Okay. And then okay. Great. What is there a mic? Do I need to hold it?
Rohan. Oh, it's under there.
I think.
Okay, great. So I've been hacking on this deep learning framework called Gigagrad for a while.
Oh, real quick, the screen you're sharing is distinct from the screen you're on. So, can you share?
Oh, no, I think that's right.
No, it's not sharing.
Oh, it's not.
So it looks like this. Oh.
That is bizarre.
Recording in
Okay, it says I'm screen sharing.
I think it's blank screen right now.
You might be sharing a specific tab. That's a different tab.
Yeah. Maybe it's
Maybe you should
window or something.
share the whole screen.
Yeah, I did,
that's what
right?
you did.
Entire screen.
Maybe move over your window and see if it's.
Maybe you need to enable the display mirroring things, then it's all one screen, because maybe it's only sharing that other screen.
Or can you do this out of full screen though? Maybe?
Like,
Yeah.
like this?
And then just make it large.
Okay. Is this sharing?
Not that I can see.
No, it's still sharing nothing. Turn sharing off and back on.
Stop sharing. Share screen. Entire screen.
Get a full screen here.
Oh, levels of full screen. Oh man, I didn't think of that. Wow. Okay, now turn it off. Sorry about this.
Entire screen. Allow.
There we go.
Okay, it works
Now it's
now.
working.
Okay, if I switch to my terminal, does it work?
Yeah.
Yeah, it does.
Okay.
How many software engineers do you
Okay.
Yeah. Okay, so back to my presentation. I've been hacking on this deep learning framework called Gigagrad, and before it was only generating C code, and now as you can see, we've added a shiny new metal backend called backend metal, and so as you can see by the kernel keyword, generates metal. And so how does it perform on a matrix multiplication? So you can see it generates these two files, scalar and metal. And if we give it a few seconds to benchmark. Yay! We can see the metal backend takes 57 milliseconds and the scalar one takes 81. So we've got a speed up, and this metal backend is still quite inefficient. There's a lot of extra stuff we could be doing to like tile things more efficiently, or use more threads, or one big one is every time we invoke it, we recreate the whole command buffer thing, because that's the only way we could get it to work on short notice. So yeah, lots more improvements coming. And shout out to Chris for providing me all the code samples needed to make metal work, because I wouldn't be able to do that without him. And
Can we see the code diff between scalar and metal?
yes, let me. Okay, so this is the metal. This is the generated metal code. As you can see, it's quite ugly. And then if we look at the scalar code, it looks pretty similar, but notably, this has the kernel keyword here, and the outer index is the the thread position in the grid. And so yeah. Otherwise, they're pretty similar. So actually, the code gen part was not the hard part. The hard part was figuring out Apple's crazy metal APIs. Any other questions? Oh, yes?
How does it compare to like TinyGrad or other similar sort of libraries?
Right now, it's much worse, but maybe I'll say this on record. I think I'm a better programmer than George Hotz, and so it eventually will be better than TinyGrad.
congrats to Sasha. Okay, Squat by Tiger, Andrew, and Josh will present a new benchmark for AI code generation.
I think you're still.
Yeah, Sasha, if you can end screen share, that'd be great.
I even closed my computer.
Cool. Hey, we worked on a tool called Squat. It's a play on words. It's a bench, like a benchmark. Squat. And for context, we're working on an AI code generation company called Exponent. And one thing we realized through the process of working in this is that there's no really good code generation benchmark. State of the art is kind of SweetBench, and SweetBench is kind of a huge repository of different GitHub issues and diffs on those GitHub issues. But we realized what you actually need for a really good coding benchmark is an infrastructure project. You have to be able to take a wide variety of open source repos, which usually run Docker or like some complex systems, and then actually be able to iterate with the code and run the code to get feedback, and then like finally have some eval metric to run also on a machine in order to realize if you did the task correctly or incorrectly. Versus SweetBench kind of just sees if you edited the correct patches or edited the correct files or not. So we ended up going down this like big info rabbit hole of like how do we get some like DSL where we define a bunch of repositories, set up commands, a simple prompt, and then some evaluation command that returns exit code 01, and like run that really fast on like a huge fleet of machines, get the results back, and also make it pluggable for anyone's agent to go work on those things. And we realized what we need is like some way to run Docker and Docker on the cloud, but also run that locally. And ended up going a bunch of rabbit holes of using like Dagger, which our friend over here works at, and then we ended up working on fly.io. So we didn't get it working fully end to end, but what we did was we defined this DSL, we got it working locally, and then we got a fly.io machine to basically be able to run up Docker Compose, initialize a repo, and run the open source repo's PyTest suite. And the idea is we can just now load an arbitrary Docker container on top of this that the agent runs in. It would make edits to this file system. We would run the eval command on top of that, and then we will see if the exit code 0, and so you pass the benchmark test. If not, you fail. And then we can ideally run this on like a fly.io suite or like a set of machines and give people results back. So it's a little more polished to do, like putting all the pieces together, but that's basically what Squat is. Any questions?
Yeah, I guess, are there any implementations of code gen systems that will break this? Like, is it restrictive in any way to the kind of systems people can submit?
It kind of is. Ideally, you have some entry point where like you can like Dockerize your agent and then it can run within this machine. Let's say you have like a Devon-like system where they have like a bunch of custom infra. What you would have to do is that Docker entry point would probably just like mount this machine's file system onto Devon's machine. They would do all their stuff and get back the patch files, and then we would run the evaluation command. So I think like Docker is like a sufficiently flexible enough abstraction where any system could go and hook in and then like do their stuff and get stuff back onto the machine. But this I think is like the format we would like specify, like as long as you do your work on this machine and then we run this command and it returns a 0-1, you should be able to do your work within that.
I see. And is Dockerizing agents like common way to like?
I mean, you have to Dockerize the agent. It's just like the entry point has to be Dockerized, right? So even if like you end up shelling out to some other system that you host, at least you have like some way to like come into Squat and like run your stuff.
Yeah, do run it.
Rohan. Sorry, I didn't catch what the issue with SweetBench is and how this is resolving that.
I mean, you can probably speak more to it.
SweetBench just isn't runnable. Like anyone who wants to, it's just a data set. And so in order to actually make changes to the code bases included in SweetBench and then verify them, everyone currently has to set up custom infrastructure to do that. And it's not trivial because each of the code bases in SweetBench, there's like a dozen of them, each of them has different ways to set them up and run them, and so yeah, that's basically.
So is this sitting as a layer on top of SweetBench then? Like it feels like
Yeah, technically you could plug in those examples, but SweetBench is, I think, is only Python examples too, and so there's, yeah, I think a lot of ways this could be extended to make the data set.
What's the language coverage here?
Anything that can be Dockerized.
Oh, it's,
Yeah.
So it's a framework for adding examples.
Exactly.
this also sort of reminds me of like the Mind to Web to Web Arena kind of diff. If you're so like Mind to Web, they originally had like you weren't able to run actual agents through it. It was just like action trajectories, and then Web Arena like 6 months later, they allowed they introduced this whole system where your web agent could actually go and interact with the websites and whatnot. So it feels like a really fitting kind of evolution.
Well, I'm not familiar with that, but
Sounds right. Yeah.
Any last questions? Congratulations. Okay, that was Squat. Hardcore Inference by Eduardo Reis will talk to us about how to generate 8 thoughts for each token. On deck, we have Kyle Morris's EzML. And Squat, can you add a link to your project or your code? Or some external representation? Hey Squat, can you add a link to your project or your code? Any external representation?
Sure.
Eduardo, you need a Zoom?
Yeah. Sharing.
Okay, yeah,
Do I
I can see
share?
that. I can see that.
Do I need to connect to?
Yeah.
Sorry. Okay, cool. So this is a educational project. I want to learn more about all these reasoning papers that are out there, and a good start is a paper that I just came on. It's very recent. It's called Quasar, and it's I guess 1 month ago. And the idea of this paper is just, it's crazy, in my opinion it's crazy, but it's super cool. For each token, they generate 8 thoughts. So it's really computationally intensive. For each token, it's not for like the task. So it will leverage like new compute like Grok is doing. So speed inferencing will be a really important thing in the future. And this idea also resonates with me because a few months ago I was having a crazy idea that all of us, we do this RAG for the task, right? We do RAG and we put the content in the prompt. So that's what we do. So we do RAG for one task. But what if we could do RAG for each token? It's crazy. But as you are seeing, I speak very slowly. But if you think for each word that you say, it's basically we are accessing our memory. So we are doing RAG. And we are also producing thoughts. Maybe 8 thoughts between each word that we produce. So these things are really interesting. And then I thought it was crazy to do RAG for each token, right? Isn't it? But if you go to the original paper, the original RAG paper, they did that. They actually do that for each token, and they do that for each sentence, and they do that for the entire task. Today, we only leverage for each task, but maybe in the future. Okay, so as you can see in this picture, for each token generating 8 thoughts, there is a value model, reward model that see if the prediction is positive or negative. And my idea was to go there, download this model from Hugging Face, and just see what happens. And I just were able to run this few seconds ago, and this is the output, and it's just it doesn't work. So These are the questions. This is from benchmark. I think it's from MMLU. And the model just continued the question. So it didn't generate anything useful. And I guess there's something wrong with my code because the thoughts are not being printed here. But yeah, that's what I hacked today. Thank you.
So the idea is to do this at inference time. That is, with each word
Yeah.
that the LLM is generating, you do a different RAG query and continue to generate. But your LLM's conditioned on the query, and so its context window is constantly basically updating for each token. Is that the thought?
That's a good question. I don't know how to answer that. If these thoughts, they stay in the context length, because there might be a selection of which thoughts are useful, and I don't know how to answer that, but that's a good question. Okay, thank you guys.
Cool. Okay. Kyle Morris is about to show us EzML, a faster, cheaper way to orchestrate ML inference on H100 GPUs without using Kubernetes, Docker, or Python.
Where's the thing?
Oh, it's at the desk.
Oh.
Cool. And can you join the Zoom, by the way?
Sorry.
Can you join the Zoom?
This one.
Yeah.
Cool.
Yeah, sure.
Let me just minimize how much is incriminating. Mac does this thing where like you connect and it just shows every tab at once in the like immediate zoom. So I'm like closing 50 tabs that probably shouldn't be streamed on Twitter. Cool. I think that's good enough.
You're just saying that you close those tabs is enough for us to imagine what kind of tabs those are?
They're fine. It's just bad code. No. Okay, which file am I in? Let me see. Okay. I think I'm in the right thingy. Yes.
Share your screen on Zoom if you can.
Oh, share on Zoom?
Yeah.
Yeah, okay. Is this on desktop one, which is my one screen? Cool.
So it's right.
Good. All right. So I'm just trying to navigate. I should have like a little terminal thingy. Cool. Sweet. Okay. Bunch of stuff going on. EzML. Cool. Yeah. So my whole thing. This was like an educational project. So I was trying to like wasn't focused as much on shipping something like immediately useful as much as I wanted to like have a wide span of tools to try out. And so my goal was like, I've been writing a lot of Python for the last few years. I did C++ in 2018, like before, but it's been like a while. So I was like, could I just try and do GPU orchestration without any of the modern abstractions I've been using? So what I've got here is like the minimal demo. There's like this little binary that is made in C++ called EzML. And what it does is you can do like EzML init, and then you could say like some project name, and then it initializes a project. And the ones that get init are kind of broken, so I'll show one that like I fleshed out a little. But it'll generate a server.py file, which uses this like Flask equivalent in C++ called crow. And right now, some boilerplate code that loads a model, but what it'll do is like you'll have a config that if you specify like BERT, it'll just pull the BERT weights into your folder. And then it creates this file called .gpus, which will have a list of all the SSH connect keys. And then what you have, the whole EzML binary is just a single file. This is kind of like Karpathy's, like micrograd, where you'll do like EzML deploy, you run one command. And I have a bunch of like weird stuff on runpod GPUs where it's like preventing me from having a terminal session, and then throwing a bunch of errors because of that. But basically it will, when you run deploy, it will just go through every SSH key in the in your GPU config, push your server, your C++ server onto that remote machine, and then like run the inference server. And then on this local, on the Mac that I'm currently running, it runs this middleware file where it basically exposes a middleware server on my Mac, which has a built-in task queue in C++. Like there's no libraries, it's literally just like, there's your task. It's like, there's the thing, and then this server on my Mac will take in jobs and then spread them out across the GPUs that are defined in .gpus. So the goal of this is like, there's no Kubernetes, there's no like daemons, there's no agents, there's no install stuff ever. It's just like dead minimum. Like if you have like multiple clouds that you want to connect to, you can just be like, here's the SSH commands to connect to my like 10 different GPUs. And then you can run deploy, and then you'll just have like the kind of dream, which is, I'm not there yet, but I want to be able to like, you would take your root repo here, like EzML, whatever, some project, and you would put it on like Vercel or like Railway, and then there would need to be work done in this, I guess we'll call it like a bootstrap or bootloader thing, where it needs to like look at the machine it's currently running on, expose proper ports and stuff, so that you now have this middleware can actually be called like is effectively a fan out or load balancer or whatever to downstream GPUs. And yeah, it's meant to scale up to about 64 H100s. It's just for inference. So yeah, it's meant, the use case is if you are a indie hacker or early startup and you have weights and you want to try it in a production setting as quick as possible and like not have to pay a bunch of money, like you just have the compute. This is like the fastest like developer experience to do it. Yeah, and then yeah, but mainly I just wanted to like learn all the different tools. And so this was fun. To talk through a couple of like the main blocks I had was like, yeah, so like runpod, maybe somebody knows an answer to this, but like apparently they didn't give permission to like do certain SSH, like what is it, like terminal from code, because there needs to be some like SFTP thing running on their end, and they don't allow sudo privilege on the machine, so I can't go and like modify the like SHHD or SSHD, like whatever the heck, there's like I think it's SSHD, the SSH daemon, can't go and configure that, so it's like connecting to this machine's a pain. So like that might be an issue, is that like if you're using a bunch of clouds and like some of the machines are like not letting you customize stuff, it's not as easy to orchestrate. But like this happens with Kubernetes as well. Although I think with K8s, there's like, if the cloud provider is already running a K8s thing, then it might have specific ports or like things that work just with Kubernetes. So there's some stuff where I'm like, it might not be as simple as I thought, but like it was fun to go through and like learn. And then I think the next step for this would be like actually doing a benchmark on just like how quick can I load up things, and how quick does it compare to like a Kubernetes or Docker. But like it's a rough 10x on just like any of the single ops to load. Like Kubernetes pod load time is like, their SLA is like 5 seconds, and then like ideal is like 1 to 2 seconds. So like with this, it's just an SSH and like a push, and then like pinging literally the GPU's like IP. There's no round robin stuff. There's no weird like schedule etcd like or whatever, like caching, like log ingestion. Like it's just that. So I think this could extend to also having like basic observability, but just the whole gimmick is it's like one file or like 3 files that just do observability, orchestration, run your job, like all at once. So that's it. Cool. Yeah, that's my thing.
Questions?
I think I already asked asked one question before, so
Sure.
I'll
What's up?
give the first
Oh, yeah.
opportunity.
I just have a question. Does your dispatcher service also collect the results coming back from?
Yeah, so what it does is it injects this, like, I don't know what the term should be, but like it injects a program onto the GPU that sets up the machine for networking, runs a server that exposes on default port 8080 with a slash endpoint, and then the middleware can just post to that, and then it gets an HTTP response from the server. So it won't handle long jobs yet, but one way to extend it is in the server file that gets generated for every project to just make a task thing where it could like do a random ID, return a task ID, and then have a checking function so you could do asynchronous jobs. So that's possible as well. I just didn't get to, I kept like a very narrow design just because I was like stuck trying to make, I spent like 3 hours today trying to make Torch build on a Mac, the C++ version, because like it didn't work with Brew, and then like just that, so it's fun. Yeah.
So the most common use case that we face, especially like coming from a small team, is like you start thinking about C++ as soon as like you cannot do the scheduling and the pre-processing in Python fast enough from one thread, and it's such a pain to just like parallelize it in Python. So I switch to C++. And then like the minimal case is like we have like one machine, it's 8 GPUs, they're not fractional, it's not like there's like some cloud that does like the splitting, whatever. So the question would be, can your script properly saturate, let's say 8 GPUs within one node? So like, I just have like one SSH address for it to deploy there, run on 8 machines, then collect the parallel batch and send it back to me, maybe even into Python.
By 8 machines, do you mean physically different machines, or 8
8 GPUs within one machine.
devices on a machine? Like,
8 physical GPUs within one machine, one SSH node.
Yeah, I think the next step is like, this is where Kubernetes does like those different, well, I think they actually just look at nodes. This is one of the issues with Kubernetes is it just has this like node paradigm. So when you have GPUs under the hood, it's like doesn't really treat them as separate devices. You have to like hard code it with taints and labels and stuff. I think I would just add a struct somewhere in the middleware that is like routing to the physical device, like the IP, and then a device number. I think every GPU has a device ID, right? So it'd be something like that. There's some issues where like, depending on how caches are set up so if you hard code an H100, there's like a specific setup of caches where like you won't have impacted performance if you're doing something like MIG, like multi-instance GPU. But if you try to like load a bunch on there, you're gonna get like degraded, you're gonna have increased latency per job, but you'll have like better throughput overall. So there's like trade-offs there. Maybe there's ways to actually do it better. Cause like even the Kubernetes plugins don't address this. So like this library, like the next step could be to actually build that out properly and just like.
As a potential user, one killer feature that I would request is have support for like auto-resolving batch size, because like it's always a nightmare with using GPUs like for large-scale inference.
So you mean figuring out the batch size such that you don't get like an out of memory?
Especially like in multi-GPU setups, you can like on the C++ side, Wiser kind of slice the data, send it to separate GPUs, and avoid out of memory stuff.
Is it proportional to, as in, could you do like a sampling method where you do like an you just double and then you sample how much memory is used and then increase?
You can binary search until you get an exception.
But is it proportional? Because it has to be for that to work. Versus if there's like ragged amounts, like you say 10% of my is loaded, and now the VRAM goes up 3x versus 2x.
It's still a discrete integer
so if it's
space of batch size, so you can still binary search it.
Okay. Yeah. Cool. Yeah.
Thank you for your project.
Yeah. Thanks for the feedback.
Fascinating. Thanks, Carl. So UCall from Ash, Mark, and Victor is up. They're going to show us how to create a faster Linux kernel bypass for JSON RPC. On deck, OMNI by Terminus.
Okay, as one of the co-organizers, I should probably not be judged. That's why I'll speak freely. We were a team of 3 with Mark and Vic. Vic, say hi, and I think Mark is somewhere further. So we were working on this project, UCall, that I started as a prototype over a year ago, in like the first days of March 2023, and it was like one of my first attempts in many years to write anything network related. It surprisingly got like some local success. I posted it on Hacker News, and the thought that I had there is that we had very lightweight models that we wanted to run on very powerful servers. The throughput of our GPUs was a lot higher than the quality of implementation of the most Python networking libraries. And then I had like this super stupid example. Let's say you have, I'll try to pitch it as an AI startup, so sorry for that. Let's say you have a lot of AI agents. AI models, LLMs, are surprisingly stupid at counting numbers, probably just as bad as humans, so anything like beyond 2 digits is really hard even to accumulate. So now imagine that for every stupid piece of work that your computer can easily do, your LLM would end up calling function calls. So let's say you would end up building a function that just like takes and sums up 2 numbers, and it may look something like this, where you implement it in Fast API. It's an endpoint called sum. It takes 2 integers and returns a sum, as basic as it gets. So I benchmarked this on a maxed out i9 MacBook Pro at a time, which is like a $3,000 machine. The call latency was 6 milliseconds, which is practically criminal. And then you start asking, why is it so bad? And then you find diagrams that look like this and explain part of the puzzle. So Fast API, it wraps into Starlet, into Unicron, and all of this is Python. And Python is just like horribly slow, as we all know. And then even in C layer, there's like so many abstractions layers in the networking. At least like 3 of them should be squashed into one thin, like 2,000 line long implementation in pure C. So that's what I did. I implemented this library, and it looked good on paper. So we went from so I later ran the benchmark on a Linux machine, got from 6 milliseconds on Mac to 1.2 milliseconds on Linux, which is still criminal. I re-implemented this with the library called UCall, got 60, 40, and 22 microseconds for different kinds of backends, which was 70x throughput improvement, 50x latency reduction, and then I forgot about it because we had a lot of other libraries to maintain, and this was like a good proof of concept. And then people started showing up, and some of them started using this library. And a few weeks ago, I realized that there's a Fortune 500 company that uses a library of mine that is super buggy. It was just like a proof of concept, and moreover, they're not using the main branch, they're using the development branch. And the development branch was nuked by a junior employee. So then I thought, there's like some peer shaming that's about to happen because this library is approaching 1,000 stars. And I always give crap to projects that are like super popular but never work. So I was about to start giving crap to my own work, which was very scary. So today, with the help of guys that crossed 1,000 stars, but hopefully it became a little less crappy, let me show you what it does. So here we have a machine which is a Sapphire Rapids-based CPU on AWS. It's relevant because Sapphire Rapids covers all the AVX 512 instructions, including the FP16, which doesn't matter here. And then we implemented a bunch of different tests, unit tests, to cover all kinds of functionality from Fast API, how you pass JSON stuff. And what you can do with this, for example, you can build a server that has 2 endpoints, for example, like set and get, like Redis. And Redis is a huge, super powerful company that does in-memory databases. So you'd think it's like super fast, but now the networking stack is the bottleneck. So the question is, if you have like this tiny, super buggy library in a couple thousand lines of code, by what margin can you beat Redis? The answer is by significant. So we re-implemented a lot of the stuff that didn't work. We made it work. I implemented a tiny server that now has like 12 endpoints, including set and get, in C++ over std unordered map, which is standard libraries associative container, notoriously slow as well. But later we got to kind of polish everything, and we now still have a nuked library. Don't get me wrong, it still doesn't work. Even though I can run the PyTest and it says passed, 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 passed. This is me being very good at faking stuff. But at some point during the day, we got part of the benchmarks working, thanks to Mark. The most impressive number that I totally didn't expect for us to get there today was that we decided to deprecate the code and like the attempts to make it compatible with Ubuntu 22.04 and the Linux kernel 5.19 and older. Instead, we upgraded to 24.04, got to Linux kernel 6.8, started upgrading to zero copy functionality in IOUring, and on a single CPU kernel, single CPU core, we got a measurement of 1.5 million requests per second handled on single CPU core, which is not bad, I would say, assuming this is JSON RPC. So this is a text-based serialization format. So yeah, now neural networks can count numbers pretty fast. That's it. Thank you, guys. There's still a lot of work, but I'll continue it with new collaborators. Thank you. Yeah.
What was the tail latency?
Oh, we never got to measure the distribution of calls by latency. You should have seen the repo in the start of the day. I mean, it was bad.
And did you saturate the device?
I think we did, but it's still like a virtual NIC. It's not a hardware-based benchmark. So for hardware-based benchmark, ideally, the way I would do it today, I would spin up 2 instances, and I would get them on some GPU cloud. It's very hard to get like high-quality InfiniBand on third-party servers. Generally, you just go like with NVIDIA-based AI servers, the DGXs, the H100s would have like 200 gigabit or 400 gigabit NICs.
Yeah, but the point with that was like if you didn't hit like throughput saturation, then like your latency is gonna look artificially better.
Yeah.
You need like the back pressure so like you understand the
Of course.
distribution.
Yeah. So here we kind of try to measure, I would say to a certain extent, like the problems we have in our like very obvious software layers. The next steps would be to finalize the benchmarks across all programming languages so that we can stress test different clients and maybe like different server implementations, run it on real hardware, real NICs, that get the tail of the distribution, see how far it goes, and then maybe publish a report.
Cool.
Any other takers, questions?
So since this is a fast API comparison, will there be like any Python bindings for it, or?
Oh yeah, it is compatible with Python. So it looks very similar to Fast API. Let me show it. So we have Fast API server, which is here, and then let's open UCall server.py. So I had a C++ server implementation, but I also have a Python server implementation. So in Fast API, you would write something like this for eco-server if you're using Pydantic. In C++ server, in UCall server implementation, I just like keep the decorator and I can infer the contents of like the JSON payload. I just wanted like a Fast API to work with payload arguments rather than HTTP style parameters in URI, which I think is a bit error prone. And then the same applies to all other kinds of arguments. More interestingly, for machine learning researchers and engineers who hate serializing images and NumPy arrays when they pass them to servers, this library out of the box supports rich types and most common libraries in Python, so that even like for JSON, we would do like the base64 serialization and deserialization on our side and convert the binary data into your favorite library package compatible types on the fly. Okay. Thank you.
Very cool. Okay. So by Jeremy is up on a new mathematical computational notation. Lantern, you are on deck. Okay. So, I'd intended to do a number of things the Hardcore Systems Hackathon, which involved one, the creation of a new math compiler for compiling this new mathematical computational notation. But overall, the thesis is one that's been near and dear to my heart for many years, which is an attempt to merge basically the best of mathematical and computational notation into a single representation that can be used both as a programming language and as mathematical notation that one would write, teach children, use in order to discover new proofs, but which would allow you to execute the mathematical notation that you write. So if I take a photo of some math that I've just done, I should be able to feed that to a machine and have it execute it as code. Similar story, if I write code, it should basically function as mathematics that could be written. And the thought is researchers who are interested in inventing new computational algorithms can now execute the mathematics that they write in a direct way. Mathematicians and computer scientists can basically engage using the same interface. And the thought with the math compiler was that that would be the central part of the system, but actually it turns out that Claude is a fantastic math compiler for sort of first attempt. So I'm mostly focused on notational improvements. Sort of bear with me, but actually it's quite complicated to figure out all the notational improvements. So let's start by asking a few questions. So one, what is math missing? So number one, control structures. So in a standard programming language, you will have a lot of conditionals, if and else, which allow you to determine what subset of code is executed. In a mathematical notation, you'd like to be able to simply describe that. And those control structures, you'll see examples of those. State and side effects. So it's essential to basically be able to create and maintain state inside of your mathematical notation. That means you're going to have to assign some content to variables and have those variables be modified over the course of the math that you're writing. Often in math you will execute algorithms like long division, for example, where you represent the state transitions as equivalences. But you'd like here to have basically assignment of state to variables and be able to modify those variables without explicitly showing how their contents are being changed. And then certainly like execution versus description. So typically math is just sort of a very purist, stateless description. We'd like to basically be able to switch between like execution and descriptive modes in our mathematical notation. So this is an example of some of the basically notational improvements that I made to sort of basic mathematics today. And so, the language here is called OMNI. This is a basically improved version of mathematical notation that includes a few computational ideas. So here you can see basically this bracket notation. Let me make sure I do this. So I'm using this bracket notation to represent a loop. And so, if you have a single bracket, you're basically using a single loop. If you wanted to have some like nested looping, you could basically add multiple brackets, but basically what happens within the bracket occurs with a number of times that occurs with this superscript. So the superscript here is just claiming that you're going to loop 10 times over this particular change in operation. So in this case happens to be doing addition, so it's akin to a summation, but you could have included any mathematical operation inside of this equivalence claim, and that would have let you basically iterate over whatever kind of transformation you had in mind. Now, using a superscript to represent iteration means you can't use it for something like exponentiation. So the distinction here is basically when you're doing this iteration, with the bracket notation, superscripts represent a number of iterations as opposed to representing exponentiation. There's a basic implementation of this in Python code down here. So basically, this maps to this equivalent Python code. There's a sort of intermediate like LaTeX representation. So a big question that I was hit with immediately was, how am I going to represent this sort of mathematical notation when typing into a computer? And LaTeX obviously gives you a pretty comprehensive way to represent arbitrary mathematical operations. This is the equivalent LaTeX representation of the mathematical notation that's been invented here. Now, it's ideally the case that we'd be able to write this quickly and efficiently. So a part of what I recognized I would need to do is to have some like really keyboard-friendly mathematical notation. LaTeX isn't that friendly. There are a lot of words in here like text and let, and all of that boilerplate builds up and is sort of frustrating to type. When I was in college, I got really good at typing LaTeX quickly because you could take notes in tons of classes, but I think it's really not ideal as a notation which is supposed to improve your ability to think effectively. So there's a secondary project which is basically find a way to type mathematics that's fast and effective on a computer. But this is one example. I ended up using my company's product to basically create a research paper around a ton of the ideas that are here. So the paper is called Integrating State and Memory into Mathematical Notation for Computational Processes. And I guess it's linked in the spreadsheet, so you can check it out, but I'll just show you sort of a brief overview of the paper here. It does cover updates to sort of state and memory and a high-level set of principles for the new notation. It details control flow, function calls and how they'll be represented, looping, data movement across access notation, and a wide array of other basically modifications to how to write algorithms, do induction, execute various kinds of proofs, etc. And as a final example, basically, okay, sorry, I need to get back to my presentation. Okay, just to finish things off, so here are two examples of basically using novel notation. So this is how to do a mathematical proof with this stateful notation, with an example of, in this case, the Euclidean algorithm, using assignment and looping in basically what is practically speaking a sort of stateful proof. This is an example of a graph algorithm like Dijkstra in what is like a very sort of algorithmic kind of notation. So, often if you see an algorithm in an algorithms textbook, it'll look a little bit like this, but this also, includes a lot of assignment and operators. And so, sort of constitutes a way to describe a graph algorithm using OMNI. Thank you.
Yeah, so you said it's the Euclidean algorithm. Like for your proof, is that like a strong induction, or like how exactly is looping used to do a proof? Like, is it like for all integers, like loop and assert truth, or like I'm just trying to wrap my head around it. I've never.
Yeah. So it defines two integers A and B, and it loops for sort of while B is not equal to 0. So this is a while and while notation for basically modifying A and B continually, where basically B is continually being assigned to A mod B, and eventually it terminates.
Okay.
Yeah. Questions?
Oh, so I'm loving the concept. My name is Michael. I actually did a lot of work in AI and education. And I served on an elected school board, but like one thing that struck me about this was when I first kind of looked at this nexus, like intro to computer science classes kind of teach this stuff to people for the first time. I find that kids who did a lot of math and maybe did a lot of stuff on their graphing calculator, they're like, wait, this notation here is kind of similar to the mental structure of just programming my graphing calculator. So I'm wondering if I'm already thinking about how do we integrate this into like even elementary school level math education to start getting kids thinking in this kind of notation so that they can kind of learn math and CS at the same time.
Yeah. I guess that there's this sort of for all, which the upside down E symbol, which often feels like a computation symbol, and I remember using that in my math course and thinking, oh, this reminds me of a programming language. I think there's an educational component to the inspiration for this. So the major inspiration for the language is when I'm implementing ML algorithms in Python, it becomes very obvious what exactly is happening, and the same representation of that algorithm, like say it's expectation maximization or principal components analysis in mathematical notation, typically feels like egregious. It's substantially more complicated. It's much less clear like what exact computations are happening or like what is happening in terms of the algorithm. Whereas if I've implemented it in code and I go back to the math, it feels painfully obvious. And so I would love to have a notation that captures the best of both worlds, which is the mathematical notation which allows you to make proofs happen, which is abstracted, which lets you isolate variables and operate on those variables in a direct way, and at the same time get the clarity of computation, which is very explicit about exactly what's happening and communicates to me, a level of intuition about an algorithm so that I can be creative with it.
I think I have a bit of a comment/question. So I think in the crowd there's a bunch of guys who wrote their own languages at specific points in their time, of their life, and runtimes and compilers for them. And I think we all had this problem of not having, let's say, language models as parrots that can repeat after us. And the problem that I faced a lot was that you define like a language rule, then you end up writing a lot of programs in it, and then you see where it breaks in terms of like the structure of the program, where it starts looking ugly, where it's like inconsistent with the rest.
Yeah.
So how hard do you think would it be, let's say, to use this new ability of like having language models to first, let's say, define a lot of possible grammars, and then let's say take 100 representative programs, or like even in Python or something like this, and try to rewrite them using language models in this arbitrary grammars, and then let's say have human eval or just even machines with some stupid metric like the shortness of a program or like readability or the variability of the alphabet, that kind of stuff, compare them. Would it be like a good direction to continue this project, or do you have like other plans for it?
Yeah, I think that it is possible to like use ResearchGen to do most of the language design and also much of the testing. And it kind of blew my mind how I could have a model go through every major operation and every equivalent mathematical representation of that operation, and given like 4 or 5 examples of existing notational improvements that I've made, suggest notational improvements, and then create a sort of suite of basically real examples of code snippets that are unambiguously tied to like that new notation. So it feels like the test suite can also be, in part generated. And then the compilation step. So basically, I was always worried like it's going to be really complicated to build this math compiler. I looked into math compilation libraries 2 years ago, and they all looked really gnarly. Going from LaTeX to math even feels quite complicated. There's so many ambiguities, but it feels like an LLM can stand in as the compiler in a noisy way for the process of developing the notation. And then you can, once you have a totally unambiguous notation, like write a proper compiler that is totally unambiguous. So it feels like it just speeds the process of language creation up really dramatically. Yeah, on a number of fronts. So I'm a big fan. Cool. Last question.
Yeah, I agree with the sentiment of like, I think a lot of us when we were learning math, we were like this looks like symbolic CS. And I think I remember especially one time thinking that man, we need macros for like math notations. Like so is that in scope here? Because that would be something different from.
Yeah, some meta mathematics.
I feel like you could concisely. There's so many techniques that were taught to us that I feel like if it was expressed as a macro, it would be like unambiguous. I don't know if that makes sense.
Oh, I know what you mean. Yeah, I guess I would love to think with you on what that notation would look like. I think that Lisp and its variants attempt this in computational notation, and it would be very interesting to ask, like, what would a written Lisp look like? Yeah, similar for templating, like what would templating look like? Yeah, I'd love to chat with you about that after. That's awesome. Yeah, anyway, thanks a lot, guys. Okay, that is OMNI, mathematical computational language. Up is Lantern, working on Postgres vector search. On deck, last but not least, just Devon. Let's wait for Lantern. Are you gonna call?
Thank you, guys.
All right. Hi, everybody. So yeah, I guess I'll start with this. Kind of for context, I don't know what people's relationships with Postgres are around here. We did this because we really like the Postgres world of things, and the goal with this project was to bring what we are building on top of Postgres, which is Lantern, and it's a platform on top of Postgres that provides better support for LLMs and vectors. The idea is people know how to deploy production things on top of Postgres, and so we are also adding more functionality on top of this, using it as a platform. And we wanted to basically give a way for everybody to use what we have built, and we have used usearch for our extension, for our Postgres extension on top of Postgres as well. And the goal with this is that we want people to be able to start using this even before having any servers. They come to our website or they come to wherever the project in GitHub is, and they can immediately click a button, and just as they try our front ends, they can try this out. Thankfully, a lot of this becomes easy and doable with WebAssembly. So our goal was to move this into WebAssembly. And yeah, kind of what we started with. There are some challenges that like we found out from before or we found out today. But one thing we struggled, so generally the way Postgres works is it dynamically loads the libraries in runtime. Initially they don't exist, and then like whenever you want to use this, you load this, and that's for efficiency reasons. But turns out when you compile things into WebAssembly, it actually ends up removing all the symbols that weren't actually needed for this build. And so when later on you go and you're like, hey, I want to load this, it's like, I don't know what you're talking about, you're calling functions I do not know where they are. So that's a problem. Postgres heavily uses processes and heavily uses shared memory. Both are concepts that are pretty foreign to WebAssembly things. Another hill we try to not die on. But kind of things we had to deal with to get this working. And we kind of got it working to the point where, so there was a previous project that had done the heavy lifting of compiling the baseline Postgres into a browser framework, and then what we had to do is make sure this loading stuff works and then bring our extension to it. And also try to build a WebRTC interface to it. So ideally the demo would be, I set up a server here and you could connect to it through WebRTC, but that's still not demoable yet. What we have is we are able to run all of Postgres, start it up in a browser, and then you can see that like when we run the Postgres command for listing all the extension, it lists our extension that we have compiled into a separate module, and it's in here. And then we can create tables, and then there isn't much to see. What's there is that it runs queries for creating tables, and then it runs queries for running search on it that are supported by our separate extension that works from inside the browser. So yeah, we find this cool because there are, like, again, you can do the WebRTC thing where we can sit in a room, turn off the internet, and we can all have a server and build applications on top, or write local first applications this way. Yeah, we can also build and try out extensions in the fly. There are over 100 Postgres extensions. This way, you could just give a link to the extension, then we could compile it in a browser to WebAssembly, and then load it dynamically, start using it, see what you can do with it. That's about it. Yeah. Any questions?
What kind of limitation do you have for the modules that you can compile for WebAssembly? Is there like a limit that the library cannot use this feature or this feature?
Yeah, it cannot use shared memory, for example. It cannot use certain kind of atomics. It cannot use certain kind of, cannot use fork, cannot start processes. Although I have there is a way to hook up fork into like emulated fork, and then you can, if you hook it up to web workers, then you can make sure the concept of starting processes ends up maps to the concept of starting a new environment with a new WASM file in a separate web worker, so that could work. But out of the box, those are the limitations.
How about like POSIX calls, accessing the file system?
No networking hasn't been merged upstream.
And like even for local file system for, okay.
Local file system stuff, Emacs scripting kind of handles a lot of it. Jan scripting, or I don't know how to pronounce it, but for example, like in this case, I think we do some DL open stuff and it doesn't complain about it. So there is like a local version of it, maps the file system in memory, and as long as you only access things from within it, it works fine.
Okay.
Right. Thank you, everybody.
That was Lantern, Postgres vector search in the browser. Last but not least, just to button. Rewrite test files to run 10 times faster in button.
So I spent most of the day fixing other issues, but decided I was tired of all of my tests running very slowly. So I decided to make them use bun, which is 10x faster.
That's for the last speaker. So can you join this, the Zoom? And, okay.
I think I have to allow it.
I think you have to restart the Zoom.
Okay.
Maybe you need to go to system preferences and allow it.
I think it doesn't let me do it with. So actually, I can just show my terminal. I think nothing else matters.
Doing allow.
Yeah, it might not let you do
Nope. Okay. Sorry. Alright, there we go. Cool. So, spent most of the day on other things, but we have a lot of tests at my company. We've got thousands and thousands of them because we have a compiler and we've got a bunch of different tools. But the typical test stack is pretty slow, especially Jest. We run this is like a small subset, but these are all really fast tests. This shouldn't take, in this case, it takes like 3 seconds, but 2.6 seconds. I'm not very happy with that. I want my tests to be very instant. Bun is very, very fast, but not completely compatible with Jest. There's some work to be improved on that, but you still at least have to port your config over. So I made a little thing to convert all of our tests to bun. So just applying this very quickly. This actually goes through and inspects all my files, figures out what feature of Jest I'm using by parsing the code, inserts the required imports, and then generates the correct bun config. So we can see here, it generated this bun config, adds some of these imports. It's doing this intelligently, so it's not actually using it's not just doing text, it's actually looking at the AST and parsing each file and understanding like what symbols it looked at and which things are globals. So you can see here where it's like using describe, it and expect. Here it uses like test, because look at these are like what do I need from bun. And then we also have like the bun config. This is all based on what I actually had in Jest. And then if we run bun test, mostly passes, and look how much faster it is. But there's one test that is failing because it depends upon some global setup scripts that we have. Jared was kind enough to build a dev branch that actually patches that and adds it in. And we run that, and everything passes way, way faster, right? We went from 2.6 seconds to now it's, I guess, 0.4 seconds on this one.
The debug build should be like 10 times, like 8, there's a big...
Yeah, and like we're getting pain from just like, this is debug build, and it still is way faster than Jest. So, yeah, that's what I did.
So is this implemented with LLMs?
Sorry?
Is this implemented with LLMs, or is it a compiler?
It's compiler, nothing.
Okay.
Well, the tests are for AI tests related, but...
Can you show the code behind the compilation process?
Yeah, sure. Sorry. So it's using our language, which is called GridQL, which is a code. It's a query language for traversing ASTs, basically. So all the complex stuff for that we already had. So the actual transform, we'll just look at fun to test done here. We basically just have to like look for anywhere that we're like using this before all feature inside of certain files in Just and convert that over after all. And then we have to look for anything where we're looking at we have to like build up the button config progressively. But yeah, it's all using our query language GridQL, which like does simple pattern matching. So we can do like A plus B here, find those. So like that's just like looking for like anything that's addition. It doesn't matter like what the white space is because it's doing all the matching on the AST. And we're able to do that like efficiently. We can like rewrite it and remove it. So building on top of that just like
It's not already implemented. Like the parsing and AST eval.
I use my libraries that we already have for that.
Cool.
Yeah.
Very nice. Any other questions? Okay. Yeah, congrats to every hacker who shipped. Let's hear a huge round of applause for all of you guys. Okay, so to take, how long do you feel like you need for
I'm ready.
judgment? You're ready? Oh, wow, okay. So yeah, judgments are ready. Basically, let's take 2 minutes to communicate about who has and has not succeeded and prep the launch. But yeah. There's pizza if you want to grab some while we wait. So. Let's go downstairs.
Sure, I would. Not today. Oh, okay. Oh, okay.
You know the guy
That's very cool.
you're not the only person.
Yeah, I love have you ever done a
Postgres is a platform.
Well, so one thing that you mentioned on the they're very easy to organize.